Hello everyone, this is Dr. Ghanashyam Gyawali, currently working as a postdoctoral researcher in Energy Storage Materials Laboratory, Daegu University, South Korea. I am going to talk entitled Synthesis of Molybdenum Disulfide for Efficient Electrocatalysts. First of all, I'd like to introduce my academic background. I completed my bachelor's program in physics from Tribhuvan University, Nepal, and I did master degree in applied physics and PhD program in Daegu University, South Korea. First of all, I'd like to talk the contents that I will talk the background and scope of this research work, methods, result and discussion part is which like a modification of commercial MOS2 or hydrogen and oxygen evolution reaction, and synthesize new different types of MOS2 for bifunctional electrocatalytic performance, and finally I will conclude the conclusion. First of all, I'll talk the different types of energy sources like fossil fuels, which are non-renewable energy sources, and renewable energy sources. As we know, fossil fuels are very harmful. If we continuously use these types of energy sources, we will definitely finish in near future. Our dream research focus is to development renewable energy sources like hydrogen energy, which are like usable by electrolyzer, fossil fuels, and storage devices like batteries, supercapacitor. These types of energy sources are green energy. This is the scope of this research work. Actually, we plan to develop a hydrogen. So hydrogen can develop by using different types of methods, but we choose water splitting because it is very effective, promising, and satisfying strategy. But during the water splitting technique, so over potential which restricts the efficiency of energy conversion. To remove the over potential, to reduce the over potential, we need to use electrocatalyst. Up to now, platinum, iridium, ruthenium based materials are most usable, and however their high cost and scarcity affects to the large production. So we choose the MOS2 for the to replace the this very expensive materials. So MOS2 in the pristine structure, it cannot give the best performance for the electrocatalyst. So we choose different types of technique to modify, like phase transformation, heteroatoms doping, nanostructure engineering, defect engineering, and so on. We know hydrogen is most usable element, so it is usable for the development of the electricity and like to generate the power, industry and manufacturing, residential heat and building, and so on. Water splitting, during the water splitting in anode and cathode, we need to use catalyst to increase the reaction rate. If we use same materials, we call bifunctional catalyst, that could be the better for the electrocatalysis performance. So we need to use different types of catalyst, as I already talked: platinum, ruthenium, iridium. These types of materials are based up to now to increase the reaction rate. However, like they are very expensive and rare element on planet Earth, and they are poor bifunctional activity, which limits its wide application. So to replace that types of materials, we choose MOS2. MOS2, it has a high electron mobility, it is very low price and elemental abundance, and similar free energy to platinum. That's why we choose MoS2. However, MoS2 in the pristine structure, its edges parts are covered by inert sides, and it has very poor conductivity. So it needs supportive materials or further modification. In the beginning, like we choose commercial MoS2, we choose different sizes of commercial MoS2, and we studied and compare their performance. And we also modified the commercial MoS2 by using different types of technique like plasma treatment, heteroatoms doping, and so on. We can clearly see in this figure plasma treatment, which has a high energy to bombard a surface of MoS2, and which cracks and holes to expose edges or kick off the sulfur atoms and produce sulfur vacancies in MoS2, and it can enhance the conductivity, wettability, hydrophilicity, and this technique also can support to change the phase structure of the MoS2, which can change from 2s phase to 1,2 phase, which is semiconducting behavior to metallic behavior. And we also developed the flower shape of the MoS2, which has very high surface area and enhanced the conductivity, and which has the too many active sites compared to the commercial MoS2. This is the SEM and TEM images for the flower shape of the MoS2. We can clearly see the morphology of the synthesized MoS2, and the study, like in the pristine, in the beginning stage, it has 2s phase, which is a semiconducting phase, like this SAAD image, which shows the hexagonal structure, that means 2s phase. And these are the EDS mapping, which can shows the elemental composition in the synthesized materials, MOS, and nitrogen also. We doped nitrogen, can clearly see. And we further characterize the synthesized material by using different types of technique. Figure first shows the XRD, X-ray diffractor, by using X-ray diffractometer, and we can clearly see after nickel doping the additional peak shows, which means different types of phase, which was changed phases like from 2s to 1t. And second figure shows the Raman spectroscopy. There are additional peaks where appear after nickel doping, which means which can also support the phase has been changes. And figure C, BET measurement, like to find the surface area after nickel doping, it was increased. And also figure D shows that the porous structure of the materials after nickel doping, the porosity size has been increased. And this is the electrocatalytic performance of our synthesized MoS2. So we can clearly see hydrogen evolution reaction. It was very low over potential after nickel doping, and like it was we investigated at current density of -10. It was 0.17 voltage of the over potential was appear in acidic media. And in alkaline media, we performed the OER, oxygen evolution reaction. It was also lower over potential was appear. So I can conclude the this research work, actually, as I already presented, we investigated of size effect of MOS2, especially small size give the better performance for hydrogen and oxygen evolution reaction, and plasma treatment which improved conductivity, surface area, and enhanced the bifunctional electrocatalytic performance. And we synthesize the flower-like shape of MOS2, which has too many active sites, 3D structure, which exhibits good stability and reliability. And we did heteroatoms doping like nitrogen, nickel. So after doping, the phase was transformed from 2s to 1t. And like the phase transform, the enhanced conductivity, created additional active sites, and rapid electron transfer, metallic features, which is bifunctional electrocatalytic, improved activity. So I would like to acknowledge, like, thanks to my supervisor, her PhD supervisor, Professor Harking Jong, and their support, and also the physics department in Daegu University. I'll also thanks to all my members, seniors, colleagues for their help and support. Thanks also goes to my family and friends, and especially for the funds, Basic Science Research Program, the National Research Foundation of Korea. Thank you for your kind attention. Thank you.